Okay, so we'll get started. I just wrote up a summary kind of table of some of the gas concepts. This is a little bit ahead of when we're going to start talking about gas reservoirs in a couple of weeks, but we can reflect on it to it. So this TCF number is, like I said, the start of a marginal field. Now the gas field, the gas wells in the United States that there's so many of, that's kind of created the partly not really the gas fields, but typical gas U.S. shale well has about 10 BCF. That's a good well, and that's about 0.01, I think, TCF. So you need 100 of those wells to make, what you can probably produce in a marginal gas field with 3 or 4 wells. 10 would be a major, considered a major, close to a giant gas field. Probably Ormen Lange, I think the Norwegian field is probably around that number. Troll, the largest gas field in Norway, is about 40 TCF. And then we've got these really super giants or monster fields. There's one in Russia as well. I don't remember the name of it, but it's, I think, in the 200-300 TCF range. Okay, so let's kind of get down to talking about the constant volume depletion test. And the original presentation of this was by, I think, a couple of guys from Core Laboratories. Rudelberger, I don't remember how to spell it. Sounds German-ish. And a guy named Heinz. And they actually presented the experimental technique and the method, and they gave an example, and the example was actually a near critical oil. It wasn't a gas condensate. So just kind of historically, it's kind of a near critical oil. Example. The examples in the paper that we wrote, evaluating constant volume depletion data, I think that example is from the Ekofisk area. I think it was the Albushel field. The experiment is conducted at reservoir temperature only. You would never do this experiment at other temperatures. It starts at the saturation pressure. There's typically 5, probably at the minimum, to as many as 8 depletion stages. The higher the saturation pressure, the more stages. Okay? For a gas condensate fluid, the CVD test itself is very similar, if not almost equal to, the expected depletion performance of really any reservoir rock, it doesn't matter what kind, any reservoir containing the gas condensate mixture that we're studying in the CVD test. So what I mean by expected depletion performance. Well, if we plot versus average reservoir pressure in the reservoir, or the pressure in the test, and we look at for the reservoir performance, basically the producing oil gas ratio, just make this. Or from the CVD test, if we plot the mole fraction of C5 plus. Okay? We mark the dew point pressure here. Then what this is going to look like is that it's going to be basically constant here. Let's say up to the initial reservoir pressure. So we're starting here at the initial reservoir pressure. And as we produce from the reservoir and the average reservoir pressure drops, the producing oil gas ratio will remain constant. Okay? Because everywhere, pretty much everywhere in the reservoir on a whole, it's still above the dew point. And this value here is this initial solution oil gas ratio. Or if we're talking about the CVD test, this is the initial composition of that, what we put into the PVT cell. It's what we charge. That would be, that's what we fill the cell with. Okay. Now the CVD test starts at the dew point, so you wouldn't necessarily have the points above the dew point, but obviously the composition is not going to change if you're in the single phase region. So, okay. Now, as the average reservoir pressure drops below the dew point, liquid will condense out. Okay? Just as you take hot air and you touch it to a cold surface, you condense out drops of water, right? In this case, you drop below the dew point pressure and you get liquid drops coming out of the gas, sticks to the rock, doesn't flow. Okay? And so what you see at the surface, because this is what we're producing here, what you see at the surface will start going down. Probably monotonically down as far as you drop the pressure. If you went to really low pressures, you might see the producing oil gas ratio go up again. Probably not. So I'm just going to kind of sketch if you happen to go down to low enough pressures, you might see this kind of kick. But then you would have to really deplete the reservoir down to low pressures. Now, it is possible, and it does happen, but it's not common. Now, if we plotted the C5 plus content in the gas below the dew point, we would get something that looked just the same. I mean, the shape would be very similar. I'm just going to make the shape look the same. The magnitude, of course, this is in barrels per million standard cubic feet, and this is in mole percent. But it's going to look very similar. It's basically going to start at the initial value, and then I'm going to put it here just a little in red. It's going to look very much the same in shape. Okay? And if we've defined it, if we define our surface process in a simplified but kind of reasonably accurate representation, as surface gas is basically equal to all of the components produced out of the reservoir that's lighter than or equal to C4, and the surface oil is C5 and heavier components. Now, depending on the actual process, this might be a good representation, or if it's a less efficient process like in Oklahoma or Texas, then it might be something like this. Okay? It's an approximation, but it's not a bad one. It just makes things a lot simpler. You can take the molar composition of what comes out of the reservoir, reaches the well, the surface, or what comes out of the PVT cell. You can take that composition and say, well, everything lighter than C5 is going to be produced as surface gas, and everything heavier than C5, including C5, is produced as oil. So this would be an approximation for a more efficient process, surface process, and this would be a somewhat less efficient. Okay? So it might be like in the United States, these shale gas condensate wells in the Big Eagle field, they don't spend much money on making the surface processing very efficient for some reason. Okay? Probably because they $110 oil when everything was in boom, they didn't care. And today they probably do or should care. The North Sea offshore processing facility will have more efficiency. It'll extract more components into the liquid. So this is a better approximation. So this is our approximate surface process. Okay? And if you do that, then what you can find is that if the producing well stream composition, if we call that Z, W for well stream, that's little z for mole fraction, W for well stream, and I for component. That's the term we use. That's what we get to the surface. We can translate that into an oil-gas ratio in a very simple form. We can say that our C5 plus mole percent is going to contribute to the oil, and the C4 minus the gas. So what you get is that you get the ZW5 plus over 1 minus ZW5 plus. This is the gas mole fraction, and that's the oil, surface oil mole fraction. Times this RTSC over PSC, that converts moles to volume in your favorite unit. And to convert moles of the surface oil to a volume, we need to multiply by the molecular weight, divide by the density at standard conditions of that C5 plus material. And this is at standard conditions, density. At stock tank conditions, 1 atmosphere and 60 degrees C. So this equation gives basically barrels per million standard cubic feet, or standard cubic meters of condensate per million standard cubic meters of gas. You have to have some unit conversions, but this is basically the equation. And so what you see is that and this thing here is more or less constant during depletion. It's not quite right, but it's not a bad assumption. More or less constant during depletion. So if you can just find that initial number, you can use it. Okay? Okay, so it ends up that this composition here at average reservoir pressure. In other words, we deplete Schleipner down, 100 bar below the initial dew point. Okay, and then we look at the producing well stream. That composition that we would actually be processing at the surface is actually quite close to the CVD composition at the CVD pressure, where these are the same. Okay? It's a very good approximation. Now it's not okay, so and since we're only in this process, we're only interested in the C5 plus because of the very simple processing, then we can say that basically from the CVD at that same pressure. This can be converted through this equation up here to RP, PR, using this equation here. Is approximately equal to the solution, because what's in the gas phase, that's only the only oil we see from there is what's contained in solution in the gas. So this is the solution condensate in the gas from the CVD test at the same pressure. So this is our solution oil gas ratio. and this is our actually producing oil gas ratio. Approximately equal. Well, actually what you're going to find is that this is going to be approximately equal. The producing is going to be a little bit less, maybe 5%, maybe 3%, maybe 8%, but it's going to be a little bit less. So this is going to be approximately equal, but it's going to be, the solution is going to be a little bit higher than the producing. Maybe by 2, that was a strange looking 2, maybe by 2 to 5%. Okay? It's money. You know, if you calculate barrels, it's going to make a difference. But it's certainly a good rule of thumb approximation. So this laboratory PVT experiment gives us the compositions of the heavies, the C5 plus in our gas. And that gives us a reasonable estimate of our well stream producing composition at the same pressure. We can convert the compositions to barrels per million or whatever unit you want to use. And using the CVD solution oil gas ratio will be a little bit optimistic, but not too bad. Okay? So I'd call it a very reasonable approximation. For doing base economic calculations and so forth. Now, because of all this, we need accurate measurement of the CVD gases removed in the test. Okay, so that's the key. We want those, because if we get those accurate compositions, then we have a good way to predict our producing oil gas ratio, which is going to allow us to predict the amount of recovery loss of condensate, the amount of value loss in the economics. Because of this, the PVT labs should, and they usually do, try to get this right. And they build the equipment and they use the equipment, hopefully with that in mind, with that purpose in mind. There's always some yahoos that don't do it, but so I'm giving you all this prep before we talk about the experiment, because the experimental procedure is extremely boring and not really too interesting. Okay? But if you get the data and it's accurate, then you have then you have very useful data to use directly for bottom line engineering calculations of revenues, economics, value, and so forth. Okay?
oil drop out in the reservoir, it does not flow. So
Yeah.
is it always the case, or sometimes it flows? Or
Yeah. So the question is, Curtis says that the condensate, the reservoir retrograde condensate, that drops out in the pores do not, for practical purposes, on the whole, okay, this is the key, do not effectively flow, okay, to the wells. Essentially saying that oil mobility is essentially zero, okay? And the question is that always the case, okay? Yes, and for essentially all gas condensate reservoirs, no matter how rich. And when we say rich in gas condensates, we mean no matter how high that is. Even if that reaches 250 to 300 stock tank barrels per million, that's about as rich as it gets. Okay? Yeah.
As we get richer gas condensates, so the liquid dropout, the liquid saturation increases above the critical.
Right. So the maximum oil volume over the oil plus gas volume from the CVD test, which is basically the oil volume over the initial volume at the initial volume at the initial saturation pressure, okay? The max value of this is around 45%, okay? For this very rich fluid. The oil saturation is equal to that value, which I'm going to call VRO CVD, times 1 minus water saturation. Okay? Which, let's say on average, is at least 20% for most reservoirs. So now we've got at a maximum 0.45 times 0.8, which is what? 35%? About. And the residual saturation to oil in general, or the critical saturation for oil to flow, where KRO is greater than 0, is typically around 20 to 30%. Okay? So what you see is that in the most extreme case, you're just above the oil saturation needed to flow. Even at this kind of saturation, the permeability, the relative permeability to oil may be on the order of 10 to the minus 2. Okay? The viscosity of the oil is probably on the order of 0.2. Okay? So the mobility of gas, which is probably kRg over mu g, which might be 0.7 because of the condensate, over 0.02, is versus the oil mobility, which is 10 to the minus 2 at the best, over 0.2, like that. And you basically start seeing that this is going to be much bigger than this, even if there is some finite mobility to the oil, to the condensate. That you basically, your gas is just going to outrun it appreciably. You know, the gas mobility is just going to be so much higher than the oil mobility. So you might get a little bit of oil trickling in, but it's not going to be a lot.
In all these PVT experiments, after each depletion stage, we wait for the equilibrium and then take the readings.
Okay, let's wait to talk about the experiment until we talk about the experiment next. So that we'll get into the experiment itself. We'll just.
But I am talking in general, like for example, we talked about the differential liberation.
Yeah.
So in all the experiments, we wait for the equilibrium.
Yeah.
But in reservoir, we continue to produce from the reservoir. So
Well, but in the reservoirs at the level of a pore size of 10 to 100 microns, you have phase equilibrium can be assumed to be instantaneous. Some people have shown that, but that's the basic assumption, that in the reservoir the gas and oil are immediately, if there's two phases, they're automatically at equilibrium. Okay. So for this reason, I'm going to say yes. Okay? And if you don't believe it, then probably the easiest way to prove it to yourself, if you've got this reservoir model describing your reservoir, which most people will have, okay, and you make two runs. You make run one with your normal, whatever you want to call them, normal rel perm curves, okay? And then you make, in green, you make a case where you just set KRO values everywhere in the model to 0. Doesn't matter what the saturation is, okay? Just don't let it flow. Now, the kind of model you would do this with would be some kind of a full field type model or a single sector model. Okay, you're not looking very close to the well detail. You're just looking in the bulk, and then you plot recovery factor of the oil phase. Okay, versus average reservoir pressure. Initial pressure, and if Curtis is right, these are basically going to be falling on top of each other. Okay? And if Curtis is wrong, then if Curtis is wrong, it's going to look like that. Okay? If Curtis is wrong. Okay? I'm willing to bet you some amount of something. Since you don't have maybe as much money, then we can do some nice dinner. You have to make me a dinner if I'm wrong, and I'll make you a dinner if I'm wrong. Okay? Okay. So it's been done many times before, and In fact, the Norwegian Eivind Favong, he got his PhD, and he was recognized by the industry for audit on, a lot of that work that was done. And basically, it's pretty much just the way it is.
And what is the reason for the increase in RP in the curve at very low pressure?
Okay, so the question is, why would this go something like that? Okay. It has to do with the K values. Remember the K values versus pressure? At low pressures, Ki, and now we're looking at C5 and heavier components, right? Okay. Basically, it's equal to 1 over pressure. Okay? So if you get to low enough pressure, those K values are really increasing significantly. And to the point where those components want to start moving to the gas, because the higher the K value, the more that component wants to be back in the gas. So it's because of that.
But if it's increasing, it means we are getting more oil.
No. If it's increasing, it means that the component wants to be more in the gas.
Yeah. So it means we get more gas, but in the curve.
Well, if you get that component more in the gas, then you'll get a higher amount of this C5 plus, right? It'll go up. Yeah. So this is the amount of the components in the gas phase. So as you get to low pressures, the K values of all these heavy components are going inversely proportional with pressure. So all those K values, the components want to be more and more in the gas at low pressure. Okay.
So this is the revaporization.
Yeah, you can call it that, but it's just it's the K values. Revaporization is just a word. It's the K values getting higher and higher for all of the heavy components. Okay. Any other questions? So then the final hour today will be just, I'll give you the procedure of doing the experiment and what's measured. So, okay.